Okay. So just to officially say, I'm recording um, this talk. Okay. And, okay, folks. Um, so I'm going to talk to you. I'm going to build from simple systems up to more complex systems and provide some insight on the different kinds of data analysis um, people apply in the science SAS community, which is whether you use X-rays or neutrons, it's not any different. It's just the kind of information you're sensitive to. Um, okay. Looks like somebody's trying to get in.
I got it. I'll let
Okay,
people.
so yeah, so let me know if you are stepping out, Luke, then I may want to minimize this to help people
Okay.
come in.
Yeah, I plan to be here for the whole thing, but okay.
Okay, thanks. Thanks. Okay, so I want to start with some idea of systems around us that can that give you some kind of hierarchical systems in nature, and many people apply this to understanding those structures. I think a lot of these we all know about it. It's just the kind of information we can pull out in the plant system. Um, the plant cell wall consists of a complex mixture of all these biopolymers, mostly sugars, but then you do have some hydrophobic polymer to help create a boundary with bugs around you, and even water for that matter, to allow water to flow through the channels and not deteriorate the polymer. And that's lignin. And then you have cellulose and hemicellulose, which are more sugars, um, which can be converted into ethanol. So there's a lot of interest in understanding, first of all, how the plant cell wall is organized, assembled, what are the interactions, where are the connections, and how can we break open so that the bugs that digest these cellulose and hemicellulose polymers can efficiently do that and create enough yield. And this is just a depiction of how a plant cell wall consists of. These are the lumens. And within the lumen is, you can think about these lumens to be um, um, more like organelles or plant cell wall. And then they consist of cellulose strands that come together to form these microfibrils. These microfibrils are then coated with hemicellulose, which is more amorphous. And then this amorphous hemicellulose is understood to create a connection, like a handshake, between these rigid microfibrils and the amorphous lignin glue, and with that creates the boundary. And we do a lot of work in trying to understand this. The length scale of these of a microfibril is about 4 nanometer. So you can, it's very difficult to image them in real space. The other option, are almost the same dimension. This is a vesicle. Lipid bilayer is also about 4 nanometer, and um, nanodiscs. Again, you have these bilayers of lipids. That's also about 4 nanometer. And then there are many different ways to parse this. I'm going to touch upon some of them. And this, what we have shown here is parsing this information all the way to the lipid molecule, different segments of the molecule, and then trying to understand how they're organized in this structures, suprastructures. So you get an idea of the structure, because if they are regularly arranged, you can see their diffraction peaks, as well as you can know exactly how these lipids are organized within the superstructure. Now, there are other neat things. Only small angles, only neutrons can do that. You can contrast match this lipid bilayer and study the structure of these wrapping protein molecules. Similarly, if you have any molecule in the lipid vesicle, either a peptide or a polymer or a protein, we can match the lipid vesicle structure by mixing deuterated hydrogenated lipids. And the mixture depends on what is the composition of the head group and where does that sensitivity with neutron fall. All this, then what else? We have other things like sedimentary rock, calcite. A lot of these calcium carbonate sedimentary rocks have biomass, or when I say biomass, is more like biological molecule in there, that organisms that build or capture carbon and create these structures. So when we study these calcite structures, especially in the deep sea locations, they have both more like inorganic material plus the organic material. So we are a proper contrast match can allow us to resolve these features from where they are coming. The other is plastic and soil. This is something we have been doing for some time. They naturally have a different um, sensitivity to neutron. Plastic is more at the lower percentage of scatter, whereas soil is a bit higher. Um, and just the motivation for why I think is very clear for all of us because of current state of plastic use. Okay, so what are the different kinds of data analysis we can apply for hierarchical systems? There's a model. Um, if you use, you could do direct model fitting, or you could do shape independent fitting. The other is you make a combination of them. And there are a lot of model fitting examples. I actually probably put in a little more than what I've listed here, one or two more. And for the unified and the composite, that's the shape independent and composite models, I'm actually uh, going to go into the package and do a quick fit um, live for you all. Okay. Um, so let's start with a, um, so I'm going to use a polymer um, which has hydrophilic and hydrophobic parts, and it behaves differently in different environments. So it's a little, it's a much easier system to talk about from a simple fitting approach to a little bit more complex. But then I get into more regular biological systems. In some way, these tri-block copolymers are versatile polymers. They also show up in packaging. They show up in cosmetics. They show up in drug delivery. So their use is so ubiquitous that we actually don't know that they're being used many times. Okay, so the pluronic is basically a PPO chain, and based on the ratio between these and the individual lengths, you can tune their property. This is a tri-block copolymer, and um, the terminal parts are the hydrophilic segments. The internal part is the hydrophobic segment. Now, at the kind of measurement we did was to vary the temperature. First, I'm going to talk about how they behave at room temperature. And this is the rough molecular weight 16.4 kilodalton. So at room temperature, this is the kind of data we get. It goes from 1 inverse to about 0.03 or 0.003 inverse. And one thing we can see here is a slope. The data keeps increasing from the background as you go to lower Q, and then it levels off. Although there's large error bar, basically it's more or less about this horizontal line, which means that you have seen the entire particle. Um, there may be not enough scattering signal, so we are not able to see. We're getting less statistics. It just means you have to take a longer exposure. If you increase the concentration, then the behavior can be different. So you're sort of limited in that aspect because you can't interpolate what is the behavior at 7% of this polymer compared from 2%. The behavior could be very different. So in those scenarios, you just need to take a longer exposure. And I don't remember this exposure time in this one. Okay, so when it's leveling off, it means that you could do a regular Gini analysis. What does Gini analysis give you? It tells you about the size of the particle, but it does not depend on the shape. It just says this is the overall size of the particle. Okay, so what does Gini analysis give us? It gives us um, a size, and the size here we get is Rg, which is about 18.3 angstroms. Now, because the data is a bit more noisy here, and this fit basically, although there are some points with reasonable error bar, is not great, and they fluctuate about the straight line fit, sort of the error is a bit higher. Now, if we had more of this data with good statistics, then the error would go lower. But 18.3, it's a reasonably good estimate of within 1 angstrom. So that's a reasonably good estimate of the size. Now, a few important points here. When we do a Gini analysis, you could as well fit data from here to here, from here to here, or from here to here, and you can get many different slopes. But how do you decide what region to make the fit, the straight line fit? And that's usually, you can think about it as the flat region in your main data till a bit into the shoulder region. Okay. Now, the reason I'm not giving a clear number there is it's difficult to. I would say you have to think about an exponential form and then think about a point in the exponential. So I don't want to get into those numeric and make it difficult. What I just want to say is you want to start to get into the shoulder region after the slope. That's basically where you're looking for. So if you see your data, you see that it's starting to slope down, you take arbitrarily a Q value, take the square of that Q. That's sort of where your Q maximum should be. Okay. But then once you do the fit, you have few other parameters to look at. One is the product of Qmax into Rg. It needs to be between 1.2 to 1.3 or less than 1.3. It shouldn't be much less than 1.3. You do need to be above 1.2. The other thing is the Qmax value and the Qmin value you use for the straight line fit. That ratio, maximum divided by minimum, this is in Q square. So you need to take the square root if you use this plot. You want it to be at least 2 times or more. Here you can see we did a large range. It was 11 factor of 11. Now, many times when you have a monodispersed particle, that means the size of one particle to the other is conserved within the error of 1 or so angstroms, then you have a very nice profile. What happens is if you actually plot this, the straight line would propagate in your data all the way, even if you do not do the straight line fit because you've already acquired your product of 1.25 or so. So you're not going to increase your Q max. So just another point, this straight line is dependent on the slope of this line, which is your RG, and the maximum Q that you're fitting to the maximum Q you're fitting, which is Q max. So if you want to increase this um, product because maybe it's at 1 or 1.1, you have to keep increasing your Q max. That's the easiest way. Now, at some point, you may find that your Q min to Q max is not a straight line, it's curved. And then your fit is not fitting your data. So that's when you need to say, okay, there's something wrong. I do not have monodispersed particle, or I'm not in the right location of my fit. So that's how you figure out about your Gini analysis. It's not very difficult to do it, but you can misinterpret. The other thing you have to make sure is you have done a reasonably good background subtraction. If your data was leveling off flat up here, that means you have a lot of solvent scattering. The solvent data, which is a straight line all along here, is going to contribute to this slope, and that would make your RG different. So without solvent subtraction, if you apply Gini analysis, you can be wrong in your answer. So there are such of these aspects. The next thing is um, to so this polymer in were basically okay. So in the Gini analysis, we know that the polymer is about 89 angstroms. If you stretch this polymer all the way, and you just basically from your chem draw, so you know what is the bond length, and you can find what is the total length, it's going to be way more than the 18 angstroms. So what does it mean? Does it fold into itself? Does it? How does it organize itself? So we think that because the polymer is not, because the size is not too big, it's possible this polymer is happy in this solvent, which is possible. You have a lot more hydrophilic than hydrophobic, 132 to 50, and you have two such 132s. So maybe the hydrophobic is able to cover the hydrophilic is able to cover the hydrophobic and sort of fold in itself and form a random coil kind of a conformation, which is the Debye flexible Gaussian coil. And that's this equation. And what are we fitting for? Is we're going to be fitting only for the RG, the size of this particle, and the scaling factor, which is how such particles exist. Now, a alternate model would be a solid sphere. Now, in a solid sphere, you would actually have just polymer collapsed and solvent outside. But in this case, we are thinking, okay, maybe there is some solvent penetrating, but it's not creating enough solvent molecules in there. There's not enough solvent molecules to behave as a bulk solvent inside the um, particle. So you're changing the scattering power of the particle had it only been polymer, but not to the extent that you're able to resolve the polymer structure inside. That's possible. Then you would fit it with a solid sphere as an assumption, right? Then this would be your model. There's slight difference between them. And then you're fitting for the uh, radius of the solid sphere, and again, how many such solid spheres are present. So that's your fit. The green one, if you see the green one, both of them are reasonably catching the solid sphere is not catching it as well as the Debye coil in the low Q. Then if you look at the um, shoulder region and the fall off, it looks like the green one is capturing it better, but then the green also does want to go much lower. The solid sphere feels like that's where it needs to level off. But you can see the solid sphere does not fit this region because the surface of a solid sphere is very well defined. That's why that type of profile falls off much faster. Whereas the surface of a Debye coil um, is not well defined. It is actually modeled as a power law 2, which means um, the polymer has a random conformation. There's no clear surface. And that's why it's more shallow in falling off. So now there are two reasons why you would create a shallow profile here. One is you do not have a monodisperse sphere. So you have different radii. Then each of these radii would be falling at different points. And if you take a convolution of all of those, that would make it more, that will move this curve up. So another way to model this would be maybe I have multiple solid spheres, but then your intensity would go up a bit. So you're putting more degrees of freedom, you're putting more fitting parameters. Yes, you will be able to fit it, but does that make sense? You want to minimize the number of fitting parameters. You're sacrificing something which is higher degrees of information, but you're at least more confident of your fit. So we go by Debye flexible coil here, saying that it's about 18 angstrom, which is very similar to the Guinier value, which is also very similar in terms of the solid sphere. But yeah, solid sphere is real space radius, whereas RG is shape independent. There's one difference there. So if you convert an 18 angstrom RG to a radius of assuming it's a sphere, it's much larger in size. And that's why this is capturing the curvature here, whereas the Guinier, the Debye coil is capturing the curvature here. So you can see that it's saying it's a slightly larger particle than what the solid sphere fit will tell you. If the solid sphere fit would say it's this, then your intensity would be much higher. So it's trying to balance the two. Okay, so probably gone a lot into it without showing my text. Okay, but it's the same point here that the bicoil has a power law 2, and solid sphere is smooth surface, so it falls off much faster at power law 4. It's crashing off, but the data is more shallow. Okay, then the go to the next step. We increase the temperature. Now the hydrophilic polymer is not as hydrophilic, or it's not, the hydrophobicity is getting much more, the penalty to be hydrophobic is much higher, and the hydrophilic part is not able to satisfy the hydrophobic interaction. So within a polymer, so what's happening, you start to have association, one polymer to the other, and you start to form these structures where you have the hydrophobic accumulated at the center, and the terminal hydrophilic chains are like tentacles to this inner core. Now, there is a model that's been written quite some time back, and what it accounts for is it says that because the hydrophobic core does not like solvent, it's going to be more like a solid sphere behavior structure, whereas the hydrophilic tentacles would be more open and it'll stretch out. Now, there is additional aspects to be accounted for in this type of a structure, because you have some interaction between chain to chain. You also have interaction between the chain and the core part of it. So those interactions also have to be taken into account when you're writing, when these type of models are accounted for. So in some cases, some of these models are a little more difficult, and we need to look for whether they are written. If they are not written, and if you have some kind of a model close to it, then you have to modify to make it, you may have to tweak it a bit to match your system. And then you can also have particle-particle interaction, and that's the structure factor. Particle-particle here is one of these particles to the other. And we call them as the tri-block copolymer micelle structure. So this is where I have that. So this is a fit of the blue curve is what I've already discussed. In 19 degrees, when we go to 28, it's not that high. You can already see there's a peak here, plus there's some oscillation. This oscillation, you can almost think of it as a form factor of this internal structure. And then this peak here is this distance. So a good way to fit this would be just to look at this peak. Where is it? It's at about, let's say, about 0.02 to 0.03. So maybe about let's say 0.025, and you take the inverse of it, 2 pi by q of that. That'll tell you what is your next neighbor distance, d. And that is our micelle to micelle distance, roughly 2 pi by d, 2 pi by q. And that's after fit, but that's to start the fit. Your initial guess could be just 2 pi by q of this value. Then the other thing we do is when we are doing these fits, we say that the core radius is similar to the overall size as a starting parameter. So at low temperatures, at least it matches. The core radius is very much the same. But then the corona radius is not clear. That's the one which is less defined. So we put it as the same as the RG as you start the fit, but then you see this has ballooned itself. It's saying that, oh, the tentacles open out a lot. Okay. But then there's another aspect to account for is when they open out a lot, is there some part of this polymer that could actually be penetrating your core? And that's this extra parameter. How much does it overlap with the core? And it says 67. So this D is actually how much it is outside the core. So it's about 67% is outside the core. So you take 67% of that, you add it to this, which is what I have here. That tells you roughly the diameter of this particle is 72 angstroms. But next neighbor distance are 209 angstroms. So let's say 210 and 70. So that'll tell you it's about 140 angstroms is the gap between them. Okay, so they are not touching each other. They're reasonably far apart. The outside tentacles are much larger, but there's some penetration into the core. And then it also tells you how many molecules have to get into this one particle to create this kind of a structure. And that comes from where this intensity is, I naught. This volume fraction is telling you how many such particles are there to account for this peak position. So it's possible not all the polymer particles here are spaced close to each other to create this peak value, the next neighbor information. And so this volume fraction may not be the exact volume fraction because it talks about how many particles are close by contributing to this peak. But as you start increasing the temperature or do anything that forces them to assemble and order themselves, then that peak will start to go up even more. And you may get more If there is less polydispersity, then these oscillations will be much better known. Okay. Another example here is on worm-like micelles. So worm-like micelles um, are basically, again, polymer, and the polymer will have is more cylindrical, and it can have many different nodes, and you can see that it's sort of uh, it's almost like taking a shape of the worm. And what we want to know is these polymer segments. What is their structure, and an overall structure. So that's the point we are trying to get at large angles or high values of Q. You're getting local structure. At smaller angles or larger Q, you're getting the entire particle structure. Okay, and this is some work by Bocage's group, and the unified fit is something that Bocage has developed. Um, and what they were able to apply this modeling to study the structure of amphiphilic polymers that are used for drug delivery of cancer drugs, docs, and they are hierarchical in structure. And if you don't put the drug, these amphiphilic polymers are happy to form these worm-like micelle structures. So there's a lot more opening, or their behavior to release the drug is much easier. What happens is the moment dox is being applied to this polymer, um, it transitions to an ellipsoidal fit. So these fits are all ellipsoidal. You can see the gray over here, they're all ellipsoidal fits, whereas these are the worm-like micelle fits. And unable to fit using the worm-like micelle here implies that once you put the docs, they transition to an ellipsoidal fit. But when they become ellipsoidal, they're sort of storing the docs drug and not allowing it to come out. So this is some application of how hierarchical fits can be applied. So vesicles, lipid vesicles is another option. There are different ways. Either you want to get low resolution, but be able to, you don't need high resolution information of the lipid bilayer and the vesicle, then you could use slab model. One option for slab model is the core multi-shell, where you are fitting each shell as your tail and head, and then the solvent. And the core is basically the inner, um, the tail. And the shell could be a single shell of head or multi-shell, based on how well you're going to break the head. Now, this should be SDP model. The SDP model parses the lipid even more further, and it breaks the tail into three regions, the head into three regions. So it sort of gives a far more detailed location of various things like the terminal CH3 groups, the the double bond CH location, and how is the CH2 part of the tail distributed. In the head group, it breaks the carbonyl, the phosphate group, the glycerol, or not glycerol, but the choline groups. And so this requires, so if you want to get a lot more information, it's almost like not necessarily crystallography, but it's almost like getting to that level of detail for a small angle scattering technique. Um, you need more data, more constraints, and that means you need to definitely get X-ray and SANS for different contrasts. In the slab model, you could go with one. The confidence of your fit may not be that great, or confidence of the results of your fit. The fit may be still looking very good for that one data, but you can still, different people, if they study different contrasts, they can get different answers. If you include multiple contrasts, then you can get a little better answer. But this type of fitting slab model does not need more than one contrast. It just makes the confidence of your interpretation much stronger if you get multiple contrasts. This is the core shell, multi-shell. So this is some work I was involved in. We use SACS. That's your SACS data. We didn't need to go to a synchrotron. This is from a lab source. Then we did SANS at 100% D2O, 70, and 50. So the 100% D2O, we got extra data all the way to 0.001. We can see this kind of a peak that is basically your micelle to micelle correlation peak. And you can see these oscillations coming up from that. And this oscillation here is basically from the bilayer. Next, this is at 70% and 50%. So we did a simultaneous fit, and this is your depiction of the scattering length densities from the fit. This is the bilayer. If you think about having the center of the tail head group here, another tail and head group of the bilayer. The blue curve, you can see this defines a head group. Dashed curve is from SACS. It defines a head group really well, but we are not necessarily very sure of where this boundary with the tail exists. What we are more confident is about the boundary with the solvent, because your solvent is down here. Then you go with SANS, and you can see that the contrast with the head group and 100% is not very good, but the contrast with the tail is reasonably good. So you should be able to determine the tail position from 100. But then if you want to get a little more information about the individual head groups, then you start to create some contrast by going to intermediate contrast like 50, 70. We could even have gone to 20 and then gone up and come down. The problem with 20 is signal. You have a lot more hydrogens. So you're going to fight signal to noise, which means you have to study for a longer time, but then not sure if you can resolve the head group that well. So SACS really does that job for us. So by combining all this information together, we sort of get an idea of a much better idea of the head group, this corner of the head group, and that's your tail. Okay. Now the SDP model here basically takes it does a Gaussian fit. It uses a Gaussian profile for every component. So here you can see the green is the glycerol with the carbonyl, and that's this green over here. I'm assuming you all are able to understand this is the bilayer distance from the center. On either side, we have two different lipids. If not, please just interrupt me and ask a question. The next is the phosphate group. The phosphate group is this blue piece over here. And you can see that the water is already penetrating into this place for the fit. And then the choline, which is just the CH3 part of the choline here, is this part. And you have a place for CH2. This is our CH3. And from this and from the total hydrocarbon, which is the purple, we are able to extract how the CH2 is organized. And when this is the volume probability of where they sit. But once you get that, you multiply it into the individual sensitivity to neutron or electron, and you get this black, you get these individual profiles, and you can see that the head group is far more strong, but then the tail is not that easy to resolve, but you can resolve your head group well. This is for X-rays. Now for neutron, your hydrocarbon is way below, and You can resolve to some extent the head group through the solvent, but it's much easier to resolve the tail group. And for this, we definitely need multiple fits and a simultaneous way of fitting it. There's a um, lot of details that's required. You need to know the lipid um, area area per lipid. That will sort of that constraint is required to make sure um, this box is defined correctly. That is, what is this total volume, right? Um, we are not, this is just a ratio. So we need to know what is the absolute volume that this whole lipid is going to take. Now we're going to cell wall, plant cell wall. In the plant cell wall, Volker has already mentioned it has, and also I showed in the first plot, it has many different components um, with structure that is over multiple length scales. So um, actually, before I go into the plant cell wall, I want to say that um, the organized part of this plant cell wall, which is the microfibrils, um, you can almost model them as shapes of known shapes like cylinder or spherical or some kind of, in our case it's cylinder, but if you had systems like beads or so, you know you can fit it to that. But if you have amorphous polymer, which is difficult to model to a shape, you get scattering profiles with some slope, and the exponent of this slope will tell us something about how this amorphous polymer is distributed. For that, I would like to just touch upon the interpretation of these slopes. So um, you have different kinds of these fractal slopes. One is the mass fractal. That means you're seeing the bulk structure. You see how the polymer is organized. Or you have surface, and porod is a specific condition where we say it's a smooth surface. And you can also have diffuse interfaces. All these type of um, condition morphologies will give rise to some kind of a slope, and the slope will have varying exponents. It goes from 1 all the way to 5. So I want to explain some of this. If you go from 1 to 3 in the exponent, then you're basically observing the internal structure of this particle. It could be how the molecule of the sample and the solvent are organized within the particle. And it could be a polymer, it could be just beads that are randomly distributed and connected, short path, it could be by continuous system. So let's start with, let's say if we are having a polymeric system and you have a polymer that's happy in a solvent, that's a polymer in good solvent, that's usually around the negative 1.5 power law. Then you have a polymer, when it's a good solvent, it's sort of stretched out, right? The polymer likes to talk or have more interaction with the solvent. Now you have a linear swollen polymer or a polymer which has a slight resistance. It's not able to bend on itself as much, so it's not as flexible. Then what happens is there's some constraint where the solvent cannot go. You're starting to fill the polymer a bit more in the given volume. Or in fact, I think my presentation jumps to power law 2. Okay, I'm not in the same thinking process as my slide. Okay, there you go. Now that's a bit more, you can see they're a little more stiff. I'm not able to open this out as much. That means you're filling the given same volume with more of the polymer molecules, and you're constraining the solvent from going into spaces that otherwise it would have filled. then your slope is going higher because you're filling the same given volume with more polymer molecules. An ideal condition would be when you have a polymer in theta solvent, or the polymer can go in all directions. There's no constraints. And that's in all directions. So that's your power law 2. And a power law 2 can also come if you have a branched polymer. If you have these branches happening in your polymer, but the polymer is swollen, that means there is some interaction. There's enough interaction with the solvent, so the polymer swells. Then also you would not fill as much volume. So even though it's branched, you only have a power law of 2. Whereas if you had an ideally branched polymer, then they fill more space, and then again you're going to get a higher exponent. So as this exponent keeps going higher, you would then call it as highly branched, hyper branched. That means your branch has a branch, and then your branch, if you can have multiple levels of your branches happening, just like a tree. If you see the tree and you pay attention to one big branch has smaller branches. The smaller branches are even more smaller. So you almost think of a tree which is where you go and break all the smaller twigs, then it's just single branch. That would be a branch polymer. The moment a branch has its branch, then the branch has another branch. You're filling more space with the polymer. So your power law is keep going up. You don't have enough space for the solvent. That's basically what a mass fractal says. You could also have this as a single polymer, as a linear polymer, but they entangle into each other. That will also fill the space like a branched polymer. So you can have a linear polymer and still have a higher power law exponent. The other way is if you have a process that's happening and there's some kind of a limitation in diffusion of these particles. And when the particles touch each other, they sort of stick, and then they start to associate and form a polymeric structure. And that would also give rise to a power law 1.2. So not just polymer, this could come from beads also. But in this scenario 1.8, it means there's something that's constraining it from sticking, either because it's just going fast beside it, which is like in this particular picture, or you could have nucleation sites and things come and associate, but you are limited with how much of mass transfer can happen, or which is again, in some way, you already have some branches, but then the growth is less because it's becoming bigger, but there's nothing coming nearby to stick to it. So these non-equilibrium processes can also give you this kind of power law exponents. Now you could also have power law exponents from regular dimension particles. Like if you don't have a sphere and you go to a rod, then you'll get a power law 1. If you have a sheet, you'll get power law 2. So there are many different ways to interpret these power law slopes. Having some preliminary idea of your particle helps. Can it be a cylinder? Then you should be fitting it to a cylinder. If it's a polymer, then you need to go to these interpretations in a solvent. So some a priori knowledge from other techniques will help you interpret your data much more robust. Now you can have surface, and that's another, what's the time? It's already 10. Okay, surface scattering, that's another power law, but that goes from 3 to 4 now. You've passed the mass, you've come out to the surface. Now, there are different, if you are at 3, that's actually an ill-defined spot because either you're in end of mass or beginning of surface, but it just means if you think about a sphere, but the surface of the sphere is crumpled like that. like piece of paper, you crumple your piece of paper into a ball, you have a surface that's going to be crumpled. Power law -4 is a smooth surface, whereas the other extreme is the rough surface. And a smooth surface is very well defined. Either you're on this side and it's the particle, or you're on the other side and it's the solvent. And that's your Perot approximation. Now, you may also have scenarios where you have diffuse interfaces, and that's more probable when you have permeable environments like oil-water interface. Each molecule is so small that you can have interpenetration. Now, this whole surface, you can't really call it as crumpled, it becomes diffuse at that point. Okay, so it's been quite some time. Let's get into quick demonstration of how to use, let's say, the composite fit. Okay. So here, macros. So when you click, when you, I'm not showing how to load Arena package, but once you have loaded Arena package, Jan Ilofsky has enough information on that. Then this SAS set of functions show up, and basically it's divided into data load. Either you want to load different kinds of data, or even there's an export here option. Then you do manipulation, which is subtraction of your background. And then you can even plot and see them. But at this point, then you would say, okay, I want to do some fitting. So there's different options of fitting here. The one I usually use for hierarchical is unified fit, if really I have no idea of what shapes can be there, or I go with model fitting. So from what I showed earlier over here, my talk, this one, this anisotropic. Did I not touch this? Huh. Probably did not touch this. Okay. Let's go here. So you could also have anisotropic data, right? From plant cell walls. So if it is anisotropic, it's not isotropic, then you need to do these divided into sectors where you have strong signal and weak signal. But you can see this halo. It's like as though the halo is all around, but then there's some streak on the center. That streak in the center is something that's aligned. If the sample is aligned, if there's aligned features in the vertical direction, you're going to get horizontal streaks. So yeah. Now, if you do azimuthal averaging for these individual sectors, which is the reduction software for us would allow you to do that. In fact, it automatically pulls that out. This is how you would get the red curve is from the equatorial, from the main and the wing detectors. This data actually combines main from 18 angstroms, then the main from 6 angstroms, and the wing from 6 angstroms. So it's combined all this data together. And then the blue one is for the meridional sector, okay? And now the scattering from the solvent is isotropic because it's incoherent, it carries no structure with it. It's just a flat scatter all the way. Whereas so now we say, okay, we subtract this constant background, which is the same in both the samples. And that's when you get the green and the orange. That's over here. Now, in some cases, as Manju had mentioned yesterday, if we have a good feel that the isotropic scatter, which is all over here in the meridional sector, is also present in the equatorial, right? Um, and the streak is just the addition to that equatorial, then we could do a 1:1 subtract of these two to only tease out what is the um, aligned features that show up in the green curve, which is the equatorial sector. Now, in this particular case, you can see there's a power law 1 here. That means there's something which is elongated, which we know because if you have things that are aligned, that's usually rod-like features in your sample, and they're vertical, that's what's going to get your horizontal streak. And the green curve is from the horizontal direction specifically. And they're different. We clearly see they're different, right? So that's what we model for a cylinder part. And then this we model for some kind of, so had we stopped our data here, it would mean that we're just going up. We don't know that there's a guinea, there's a shoulder here. That means there's some particle size also. Okay, so we're going back to the here, and I'm going to load. I need to search for this. So
Hey,
the load
Venki,
would, yeah.
you have a question.
Someone has a question?
Yeah.
Yeah, just a quick one. How do you what do you do with the wax data or the WANS data, the wide angle neutron scattering that you just showed with that plant cell wall that kind of like falls off at the end? I'm just curious of like.
Oh, this is still the SACS data. This is not VANS.
Oh, I just mean the even the tail end of that data you just showed for the plant cell wall.
Yeah, I'm going to go
Uh,
back to that.
like
So
at the
you
sort of.
you fit all this, but are you talking about here?
Yeah, when you get really close to sort of the tail end, I'm just curious of what that because it's
This
subtracted.
one?
So is that real? Yeah, that sort of
No,
slope at the end.
no, that's not real. That's just
Okay.
there's no. You can see over here, right?
Yeah.
It's basically predominantly incoherent scattering. So any information here is really just over subtraction of your solvent, and um, our fit usually would end over here in such a scenario. Had you got a data that kept going down because you had some coherent scatter, then you would be able to see that. Like actually in the green. Is that good?
Yeah, that's good. Thank you so much.
Okay. So now I have to search for the data. Um,
I think there is another question, right? From
Chris, okay, go ahead.
Lihinia Kumarage.
Hi,
Lihinia.
yeah.
Yeah.
So I was wondering that simultaneous fitting you showed earlier, the Sans and Sax. Can I ask which software you use? Is that SASWave or?
Yeah, you can do that in SAS View. In fact, you can even do it in Igor Pro.
Uh-huh.
Um, um,
So
but you may have to do a little more setup for that for simultaneous fits in the Arena package. But SAS View allows you to do it reasonably well. I did all those. I did that fit in SAS View.
so is that a core multi-shell model?
It's been now 3 to 4 years back I did,
Oh,
but um, after I finish this, I will
yeah.
open SAS View. Actually, I have some things saved, I think, as screenshots. I could open that to tell you how I got
Okay.
those.
Okay. Thank you.
Yeah.
Winky, I just want to let you know we supposed to give them a break. I don't know. We should give them a
Yeah. At 10.
It's 9:45. We late actually.
Oh, okay. Maybe we should do a break then, and then come back. Maybe what, 15 minutes break, 10 minutes? Manju, do you
Yeah,
remember?
it's 15-minute break.
Okay, so let's. Can we come back at 25,
Yes.
10:25 for us, which means I'm assuming if you're not in this time zone, based on how off you are from East time zone, you just need to add 1 hour or two, subtract 1 or 2 or 3. Is that okay? Okay.
Yeah.
Let's do that.
Can I still ask you some questions?
Sure. Yeah.
Okay, thank you. So I actually was trying to fit trying to do the simultaneous fitting in SASWIM. But I think I couldn't define the constraint properly, because the thickness that SAX is sensitive and SANS is sensitive to is different, the head-to-head thickness or something like that. So it kind of didn't work well for me. So I was wondering which constraint you used actually.
Okay. Um, I'm going to stop sharing for a second while I find my. Um, okay. This is what I took a screenshot of how I set it up. So I use this model core multi-shell hard sphere, core multi-shell hard sphere. You see those? and I fit. Please waiting. And then I fit the SACS data. I did not have any hard spheres, so it was just the core multi-shell M1. Whereas the 100%, 70, and 50, they were all the core multi-shell models, and that's over here. The first one is just the, I think it's the third, so that should be the 70%. Yeah. So I forget now which one is which here. It looks like M1. Anyway,
Yes.
so this is your multi-shell. I wanted to, so you can see these NANs. These NANs all say that if you look at them, they're all connected. The scale, the first one, but they are independent parameters. Radius, which is the radius of the fit. I think this is M3, so that has to be the 70%. Should have been actually 100. Anyway, that one is what is, yeah, this is the one which is fit, which is 100%. M2, which is M2 is here, that's 100%. Because the 100% had the clear defining peak for the vesicle to vesicle distance. All the others, I just forced it there. I did not really fit it. And I made that connect to that. Then I also said that the bilayers are symmetric. So the thickness 1 and thickness 2, no, thickness 1 and thickness 3 are the same, which is the head groups on either side. The thickness 2, which is the
hydrocarbon.
Yeah, the tail. M1 is SACS. SACS, I allowed it to fit on its own. Whereas for the SANS, I forced all those parameters to match the 100% data. If you look, all the parameters for 50 and 70 are NAN, which means none of them were allowed to vary. They were forced by this by fitting it at the 100%. But then the penalty for them, for this data not to fit, for this fit not to match the data, and this forces this parameter to vary. Do you understand?
Yeah, I see.
And here is how I build the simultaneous. You see, I say M1, which is your M1 is this one, which is SAC. So M1 radius is equal to M2 radius.
Yes.
So I force this is the radius to match that of M1, like that. So M3 radius is equal to M2 radius. M4 radius is M2 radius. Then for volume fractions, for the SLDs, for thicknesses, and that's how you force. You sort of tag many of these parameters to one set of parameters. So now you're sort of simultaneously fitting, because the penalty for any of these fits which do not have parameters that directly are being fit, only this piece is being fit. It's almost like when you're fitting this curve, you're using the penalties from the other curves to drive this fit.
Okay, I see.
Yeah, but then the SACS, I allowed a bit more freedom, because SACS is not the same. It will not see the same thickness.
Yes. Yeah.
So, right, that was the constraint I had to allow.
I see.
But if we could get maybe better maybe a little more data. Maybe I have to. We have to think about that more, and then we should be able to even fit these. But you can see that thickness 2, which is 22 angstroms. It's not going to fit that well. But if I force this to be 33, then it was not fitting based on the SLDs. So there were some aspects that needed to be.
Okay.
Yeah,
Yeah.
I forced the SLDs to be more like the solvent SLD and the thickness SLD too. I sort of calculated them, knowing there should be no solvent penetration.
Yeah, I
But
think I
SLD3,
was able to fit SANS data very nicely using SASVIV, but SACS data was giving me some hard time. So, yeah, but thank you.
So, yeah, so the problem you're going to face is SACS data has very low error bar. So if you're going to fit it, you may want to scale the error bar a bit more to match that of SANS. Otherwise, either you're going to fit only SANS, SACS, and you can't fit SANS because the SANS error bars are worse.
Yeah.
That is where we ran into problem. You need to soften the error bars for the SACS to match that of the SANS to give both of them equal priority. Okay?
Thank you. Thank you so much.
Okay. 5 more minutes and then we meet, okay?